Hi, my name is Donovan Lagane, and this is Physics 2211, Lab 2, Motion of a Falling Object. The purpose of this lab is to observe the motion of a falling object that starts from rest and is dropped straight down. This lab will use the concepts of Newton's second law, drag force, and the force of gravity. The observed motion of the object will be measured and will be compared to a computational model which will allow a better understanding of the fundamental principles used in this lab. Newton's second law. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, expressed by the equation force equals mass times acceleration. In this lab, we're going to use the velocity update formula, Vf equals Vi plus At, and the position update formula, Rf equals Ri plus V average times delta T. And here are the equations for gravitational force and drag force. Fg equals negative mg times j hat, and Fd equals negative v squared over v hat. Here's the procedure. First, we're going to record the objects falling from rest until it hits the ground. Then, we're going to track the ball's observed position frame by frame using the app called Tracker. Then, we'll create a computational model using GlowScript. Then, we'll take the data from both graphs and compare them over a position versus time graph. And finally, we'll adjust errors and answer questions after the experiment. Here's a video of the observed data. Wow, look at that ball go. As you can see, the ball was dropped from rest, initially at rest, and then stopped when it hits the ground. And here are the computational model graphs. So we have one with gravity and one with gravity and drag. The one with gravity and drag straightens out at the end compared to the one with gravity, with only gravity. This is because drag has an influence over this model. And for the code using GlowScript, we can compare gravity and drag. Here we have B, and here we have just different equations, just to account for different forces acting on the object. Here's the predicted versus observed graph of gravity only. The predicted graph looks a lot more straighter than the observed, and this can be due to a human error. But when we look at the predicted graph for gravity and drag, it seems to both the observed and gravity graphs seem to go more towards the y position, towards the negative y position, sooner than the gravity and drag graph does. Possible errors are it's hard to keep the center of mass using the Tracker app due to it's hard to make a straight line. The results might change due to external forces. Maybe there's a strong wind while you're recording, or the ball just shifts to the right a bit. And human errors might hinder better results from being shown. I believe that there could be better results that I could have done, but due to my ability being a human, I was unfortunate to make those errors. Questions. Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict the terminal velocity? So this graph right here is gravity and drag graph. And the terminal velocity is when, as time approaches infinity, the velocity will also it will never be zero, and so it will just be go to infinity. Imagine that the downward object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? The terminal velocity would be the same because the terminal velocity does not depend on the initial velocity of the object being thrown. Terminal velocity is based on the drag force